So let's start the session today. So again, the path that we took, we talk about game theory, about motivations, we talk about stable solutions, and then we talk about some of this perfect information game in extended form, like the three essential representation, or almost three. Then we talk about imperfect. And we mentioned that the imperfect and normal form games essentially are equivalent to some inefficiency may happen if you want to go from one to another. Here, we wanted to also go a little bit beyond that and talk about the repeated games, which is a generalization of some of the concepts that we have seen here. Good. So, this kind of repeated game has been used essentially by lots of people, game theorists, computer scientists, economists, social and behavioral scientists, as a way that we try to somehow model the real world situation, because lots of the time, in particular, for example, if you see auctions that the people are coming for advertisement slot, they are putting their bids, they are repeating this game over and over. And here, somehow it has been started with like some more typical or standard games like iterated Prisoner's Dilemma, Rochambeau, repeated ultimate ultimatum games, and others essentially, or iterated Battle of Sexes, but has been used essentially for more general than that, repeated auctions, etc. So let's first talk about the finitely repeated games. So here in the repeated game, the same game is played multiple times by a set of agents. And the game itself is called a stage game. And we can represent it, say, by normal form game. For example, consider this prisoner's dilemma. This is the matrix. And here, this is essentially one stage of the game. And like each occurrence of this game is called sometime iteration. You can say round, or you can say a stage. So the general idea is that these people, that when you are playing this multiple times, they know what did happen in the past, and in particular, they know their actions that they took it in the past, or they know the history, but they don't know what will happen in this particular one. So, in some sense, all previous iterations we know except this last iteration. So this we can call it essentially imperfect information with perfect recall, that an agent never forgets anything he or she know earlier, essentially. So in particular, know what are the actions that he or she took, and more generally, the actions that other players took. And we are considering like the more standard form that the agent's payoff function would be additive. It means that you are playing this Pender's dilemma each step, and then you will add your payoff, and the sum of that is the one that you are considering. Yes. Yes. Oh my God, thanks for that. So this is like happens in some basic stuff. Okay. Good. So So here, because it's a repeated game, the depth of this tree will be large, and it is still finitely repeated. But the same set of strategies that we mentioned, for each node that you are there, you need to decide which action you want to take, and then you will essentially do the cross product of that. So the strategy space is very big. One kind of a strategy is called a stationary strategy, that you are using the same strategy in every stage game. Of course, not necessarily you may want to do the stationary strategies, because sometimes you want to be dependent on the previous moves that you have done. So here, let's consider the iterated prisoner's dilemma with two iterations. So here, I mean, this is the payoffs. This is a prisoner's dilemma. So this part is so far is just the imperfect information game, that you are putting one is doing C or D, and then two does not know which action one took it, and then it's do C and D. And I think this should be also maybe C and D, or you can change it here. Good. After that, again, one is doing the actions. And then here, I mean, as I mentioned, one knows the actions that the previous information that he or she had it, they don't forget it. And then one is doing that, and then two is doing it again, and this is simultaneous. One and two are simultaneous, so this is the game. And as you can see that now, you can just sum it up. So if you are just coming CC and CC, so it would be 3, 3, and plus 3, 3 would be 6. Such. 6. So that's the additive case. Another case that sometimes the people consider it is sub-additive. That, for example, if you are doing this plus this, it would be less than or equal the sum of this. So just as I mentioned, so when we talk about additive, it means that A plus B is equal to C. When we talk sub-additive, it means that A plus B essentially. So C is the final things that you will get. That would be actually less than. So C would be the final utility. So the final utility would be less than that. That is called a sub-additive. And sometimes you may get super additive, like essentially A plus B would be less than or equal to C. It means that if you have essentially twice win, then you may gain much more in terms of payoff, the final payoff. See here. So AB is the payoff in each stage, and then C is your final payoff. So, but we consider this is called super additive. And this one is called additive. Good. So these are some very.
Sorry.
Go ahead.
Why might subadditive and superadditive be useful?
As I mentioned, so for example, if you can win, I mean, like think about this one. For example, in soccer, like the person who is achieving lots of goals, then also gets, I don't know, some kind of other award as well, the best player of the year or something like this. So it is not only you will get essentially your regular payoff in each game, but there are some additions that they will give it to you because you were the best player of the whole year. So this is extra utility that you will get out of the situation.
Okay, makes sense. Thank you.
And these are like a very typical thing. So it should, I mean, just always you should hear about additive, sub-additive, and super additive. You should see in practice which one is the correct thing. Additive is the easiest one. Generally, sub-additive or super additive becomes a bit harder essentially to analyze. But first, you should work with the additive. Okay. So some of the well-known iterated prisoner's dilemma strategies. And you can, I mean, just read them and, I mean, try to essentially generalize them for other games as well. So, all C means always cooperate. So always do C essentially. All D, of course, means always defect. The green one is that you cooperate until other agents defect, then defects forever. Tit for tat, that's actually a very useful one that we will refer to that. So that on the first move, you cooperate. On nth move, you will repeat the other agent's n minus first move. So essentially means that if the person cooperate, then you cooperate. If you defect, then you defect essentially. And that's a very useful strategy. There are some tournaments and things that this is one of the best strategies that you are taking, which is a natural essentially. Tit for two tats. It is like essentially tit for tat, but you will retaliate if other agent defects twice in a row. So you may have some forgiveness essentially. So that's the first, no forgiveness essentially. The second one is that tit for tat, but with some forgiveness. The tester one, I mean, the tester essentially see how smart the other guy is. Defects on the first round. If the other agent retaliates, then play tit for tat. Otherwise, just alternative, cooperate, and defect. While alternatively, because you gain something by defect, essentially. So if the agent is like... and then this is another one called Pavlov, that on the first round, you cooperate. After that, if you win, you will use the same action on the next round. If you lose, you will switch to the other action. And then I need to define what is the meaning of win. And so win means 3 or 5 points, you will get it. And lose means that 0 or 1. And again, these are very general things. It is not just for this game. You can design it for any other games. And it's very interesting. And as I mentioned, these are some of the things that you may actually use it in your real life. So these are some of the examples that I have mentioned essentially, that one player versus other. So one is doing this strategy, the other one is doing another strategy. And you can see what will happen essentially in each of these cases. So, I mean, for example, if it is a tit for tat person versus a tester, so this person is doing C, it is essentially first you are doing cooperate, then what will happen after that? Then this person, the tester, defects. Then you are doing tit for tat, then you defect. Then this person essentially, this tester person essentially, so this person retaliates, the other person, then you will do tit for tat. So after that, tester turns into a tit for tat things. So then it's cooperate, then this guy is cooperate. So this cooperate, this cooperate. You see that the tester at the beginning is just doing that. If the person retaliates, means it's like a smart person or like a selfish person, then it just go tit for tat. So it becomes tit for tat. You can just test this one, and these are like all different cases. And these are actually interesting. As I mentioned, these are really real world problem. Say, this one. Yeah, these are useful essentially for real world. Why? Say, for example, you have essentially apartment mate that, I don't know, making loud music, and then you may do the same essentially strategy with some other actions that you may make the music loud as well essentially, or you may do some other retaliations. You can take actually all of these things. So as long as the person cooperates, you cooperate. But if he or she does not cooperate, then you are also doing tit for tat, essentially husband or wife essentially. two spouses essentially. That can happen. This happens in real world. So these are the very natural set of strategies that you can do it. And as I mentioned, in terms of psychology aspects, also the people, and I'm sure there are some researches on that one, that which strategy you should take. Like if you go, for example, to some person that are help, for example, marriage or something like this, they may suggest some of these strategies. And yeah, for example, tit for two tats, that's reasonable thing to take it essentially in the, like, I don't know, because it has tit for tat and also has some forgiveness, but you don't want to be totally dumb essentially. Don't take any action. But anyhow, these are very important one. And I think you can think about each of them. What is the things, and which one is the one that you want to take it for the things. As we will discuss later, actually, some of these games, the best things, the best result that you can get, it comes out with this tit for tat essentially. There are some tournaments that is players playing each other, and that in average tit for tat is reasonable. Maybe tit for, as I mentioned, tit for two tats is maybe better for marriage or something like this. But anyhow, the other question.
Yeah, the tit for tat versus tester. Why is the tester choosing to go forward or cooperate with the third one?
Yeah, because I think that was the thing. So the tester defects on the wrong one. If the other agents retaliate, then it becomes TFT.
So yeah, the tit for tat player retaliated on the second turn.
No, so in the second term, then if this person retaliates, then it starts with tit for tat. Tit for tat says that on the first move, cooperate.
Yeah. Oh, so tester is taking the first move.
Yes, exactly.
Okay, then why is it all cooperates instead of
because then it becomes tit for tat person. Tit for tat person, if the other person cooperates, then you cooperate.
Oh, so it becomes tit for tat as soon as the other player bets?
Yes.
Ah, okay, that's the one.
Yeah.
So, okay. Okay, that is one.
Yeah, you can actually, I think it is a good exercise to go and test this one, what did happen, and get this one. That's a good exercise. Great. So backward induction is, typical things that always you can do it essentially, especially if the number of iterations and the number of players is finite, then you can use that. You can try to find a sub-game perfect equilibrium. So what is the general idea for backward induction? So essentially you will go there, you will just, this is the tree that you have. So this is the tree that you have. Some of them, I don't know. This one, you will come there to the nth level. You try to find SP subgame perfect equilibrium in the last one. And then you will just go one step up. And you know that the only difference is that when you play, then you have some points that you have accumulated so far, and that you need to consider as well. So this is essentially the algorithm for this backward induction. You will start from last round, the lowest part in the tree. This is we are assuming that essentially the rationality is the common knowledge. And then here, everyone will play their SP after action after round J. So we assume that, what is the best thing? So essentially you are doing this min-max type of thing that we talked before. Then when you do that, then you know that, okay, if I'm doing that, this is in the, for example, in the subgame perfect equilibrium here, it would be, I don't know, a 3-3. Then in this case, this 3-3 will come up. So that you have it in addition of essentially the points that you will get at the current stage things, and then you are making the whole things up. So essentially from round n, you will come n-1, n-2, and so on. This is some kind of inductive essentially. And of course, that's a reason that is called backward induction. So let's see some examples. Good. So consider this prisoner's dilemma things. So we have n repetitions of the prisoner's dilemma, and this is the matrix. So this is at round n. So at round n, this is the last round. So SP essentially would be just the Nash equilibrium, and the Nash equilibrium we knew that was 1, 1. Because if you take 1, if the other person takes 1, then if you change your action, you only lose essentially. Good. Now, for case n-1, so we are saying that if everyone plays their SP actions after round J, means here in round n, then the essentially the cumulative payoffs would be 1 plus payoff at the round J, because you get 1. This was the equilibrium that you had before. So just add 1, 1 to everything in this matrix. So it would be the same thing, just 1, 1. I mean, just add it to everything. So it would be 6, 1, and so on. So then you will find the essentially SP action at this round, which would be again this 2, 2 essentially. So these are some of the things that they have played. So that considering that, what is the thing? Then you will repeat this one. Then it would be 2, 2. So you will add it to this matrix 2, 2. Then it will become this one. So this is essentially so this 2, 2, you are adding it, you have this one. So it means that, I mean, not always it is the case. It might be some games that it may change essentially, but at least in this case, you know that the SP is to place DD on every round. And this is a stationary strategy. It means that you just do it. And there are actually some of the people have studied that whether this equilibrium makes sense or not. As I mentioned, always we can define lots of equilibrium. The issue that whether in reality this happens or not. Because there are lots of stable situations, at least theoretically. We want to see whether practically these are also some useful ones or not. And there are lots of studies on that. You can just search on that. Yeah.
So jumping ahead a little bit, the way I see a practical solution would be to play CC every turn until turn n, which is DD. Is that right?
You can repeat.
So with the practical solution here, like without being like play CC for every turn on turn n, switch to 1, 1, go to DD.
Yeah, essentially the one that you mentioned is this tit for tat type of thing. Yeah. Essentially, that's the one that in practice we will mention it. There are some studies and say that that's the one that gives essentially the main essentially payoff here. Okay. So there is some equilibrium concept, but not every equilibrium concept is useful. Essentially. That's the thing that we consider different concepts. Essentially. As I mentioned before, in the game, in the optimization, generally there is an optimum solution. Maybe we cannot find it because of NP hardness, etc., but still there is one. Then we can try to approximate it. In game theory, there is not one solution because there are two people. Everything is a trade-off. The question is that where do you want to do trade-off? Here, here, here. And that depends, to different situations, it might be different essentially.
I have a question.
Yeah.
So why did the payoffs in each matrix increase as we go backwards in rounds? Wouldn't they accumulate more points as they progress?
Yes, that's the reason that we are increasing it. Yeah. So because the points that we are getting, essentially, we are just adding it and then say that given these points, And we are assuming that everyone is doing Nash equilibrium. That's the current matrix. So what is the equilibrium is this matrix?
Okay. I was just wondering because you start off with n, which is the last round, and then in n-1, so the round before that, the payoffs are higher.
Yes, because I think you are coming down the tree. So when you are down in the tree, when you are here, I mean, first you don't have anything. This is like close here. So this one, yeah. So here you don't have any essentially things. You just play this one. But when you come here, then you may gain more essentially points, and then you will come and do that.
Oh, I see. Okay.
So because we are coming from the down to the tree, essentially, that's the win. So that's essentially this is some kind of temporary matrix that helps you to decide which action you should take in an equilibrium.
Okay. Yeah, that makes sense. Thank you.
Sure. Thanks for asking any questions. Good. So let's go. So these are, I mean, some of these for the two-player zero-sum repeated games. I mean, you can think about it why these are, some of them are not hard essentially, but need some thinking. It's not trivial. So if in a two-player zero-sum repeated game, the SP is for every player to play a min-max strategy at every round. That's it. I mean, the idea essentially comes, the whole things become a zero-sum game. So in a zero-sum game, because it has a finite thing, anyhow, it would be a 3. So you should, the best SP thing it would be to just do min-max. Your min-max strategy is the best for you if the other agents also use their min-max strategies. But in some cases, the other agents won't use this strategy. So again, this is the definition of min-max. So this is nothing new. As I mentioned, if this is a repeated zero-sum, essentially the whole thing would be a zero-sum game. So then that makes sense that SPE would be the min-max that we talk about. Now, your min-max strategy is the best for you if other agents also use min-max strategy. That is correct for any min-max essentially for zero-sum game. Because if the person do essentially some other stupid move, then it's better that you respond the better thing for that. And if you can predict their actions accurately, then you might be able to do better moves essentially. But then the question that why the other person or other agent don't use their min-max strategy, maybe they are, I mean, not that smart, but maybe they are smart. They also try to predict your actions, and based on that, oh, maybe this person is not doing minimax, so he's doing some other action. So I'm doing some other action in response to that, which is not the minimax response. So that can happen essentially, and there's no guarantee. Like if you play chess, some person, you know that this is not the best move that I'm doing it, but I want to just do it. Why? Because I want to finish the game and go for lunch, for example. And this is a husband, wife. You cannot say that, okay, I want to go lunch because the husband, wife does not feel good that in the middle of a chess you decided you want to go. But the one strategy is to just do some stupid move such that you will end the game soon and then go for lunch. And again, this one that I mentioned, you may actually try to model this game. So like the husband and wife, that one wants to go for lunch. Then it is not really zero sum anymore, because they want to make each other a bit happy, and at the same time they want to also have a lunch. So in some sense, you need to define, if you want to exactly model the equilibrium in this case, you need to actually define the normal form game precisely with the correct utility functions. So the correct utility function is not 0, 1 here, essentially. Like win, lose, or essentially like this thing. So it's not a win or lose, essentially. It's the situation is, or draw, essentially. The situation is the case that you have some other objectives in your mind. There is another one of these things that the people have considered, Rochambeau, rock, paper, scissors. This is the matrix that we talked about before. I think before we actually represented it by 2 matrices, as I mentioned. You can do it for the first player versus second player utility, or you can put it in one player. So the Nash equilibrium for the stage game is to choose each action with probability 1/3 that we talked before. Now the Nash equilibrium for the repeated game, because essentially is a zero-sum game, would be that always choose randomly one of these with probability 1/3 essentially for each. And you can say that the expected payoff would be 0 in this. So that's essentially, you may play this one. That would be the Nash equilibrium. But in reality, the people may want to use, as I mentioned, this is the best move as long as the other person is doing also min-max. But they may not do something like this, and you try to predict them, and so you may do something different, essentially. But the game essentially becomes more complicated, and the concept of equilibrium. So the equilibrium that works for one stage, it may not be the best essentially for several stages. So this is some data that we have it for this one. So there is some, in 1999, there was some international Rochambeau programming competition. You can use that link, hopefully it should exist still. So this was the round robin tournament. There were 55 programs, 1,000 iterations for each pair of programs. Correct? So like essentially, in each of these, you may get -1 or 1, say, and then there are 55 times 1,000. Okay, 54 actually times 1,000. But the lowest possible score probably you could even play with your own program as well. So in that case, would be 55 other programs, 1,000 iterations. Each of them can be -1 or 1. So the lowest possible would be -55,000, and the highest would be 55,000. Good. And as I mentioned, from the previous one, we knew that the expected payoff is 0. However, the average over 25 tournaments, it was like this. The lowest score was -36,000. The highest score was essentially 13,000. So it was not 0 essentially, it was more than that. So we can actually read more about it in this link that is here. Good. So let me just, this is it. Good. So what is this one? So now, so far, we talk about finitely repeated games that you know how many iterations. You may or may not know, but you know that it's essentially finite. You can think about infinitely repeated game essentially. So here, of course, if you want to represent it as like this kind of extensive form game, then it would be infinite tree. And you cannot attach essentially payoff to each node. Why? Because I mean, if you go infinity, then you sum what infinity number would be infinity. So whenever we have this kind of infinite things, the thing that we can do, these are again 2 common ways essentially to resolve this kind of infinity games, or when the number is so large. As I mentioned, so the strategies that they are getting, it would be infinite sequence of payoffs. And then if you just sum it up, would be infinity essentially. So that is not that much informative. 2 measures that the people will be taking, these are beyond just this concept. These are the same thing that I mentioned about additive, subadditive, and superadditive. The same thing here as well. So these are some of the common ways essentially to go around these things. One is the average reward. Here we are taking average over the first k iterations as goes k to infinity. So say that, okay, for any k, what is the average? And then when k goes to infinity, what is this one? Hopefully, if there's a limit for that. That's one way. The other one, it is a future discounted reward. That is also very useful. So you have some beta between 0 and 1. And this is some constant called discounted factor. That is very useful. It says that something, there are two interpretations for this one. So you will sum it up from j to infinity, discounted factor to the j times ri of essentially j. So these are the payoffs that you will get. So this payoff will be essentially multiplied by some discounted factor. And note that this is exponential. So in terms of number of iterations. And beta is 0, 1. What's the meaning of that? It means that it is like very far in the future, it would become 0. And it becomes 0 very fast because it's exponential. So there are two possible interpretations. You can say that the agent cares more about the present than the future, as I mentioned. So anything that so far it is there, like you care, like at the say we are starting the game, the current ones I care more because who knows whether this game happens or not for a long time. That is actually second motivation. But the first one, the other one I don't discount it. Oh, you will give me something, I don't know. In the other world, you will give me something, the people may discount that. So that's one interpretation. The other one, which is somehow, again, comes from the same things or the same interpretation, said that at each round, the game ends with probability 1 minus beta. So if you are there j rounds, it means that the game didn't terminate in so many times. And that probability would be low. That's the reason that we have it beta to the j. So that essentially, this is, again, it is a typical thing in game theory that for the future one, you may have a discount factor. For the future one, you discount it. And exponentially goes down. That is also because it is b to the j. It could be like beta times j. It's not beta times j. It is beta to the j. Good. So let me clear this. So what are the Nash equilibrium in this kind of infinitely repeated games? So generally these games, they have lots of equilibrium. Which one is good or not? That's up to you essentially. So there's in particular this theorem called Folk theorem. That's a famous theorem that is talking that, this is, we talk about two ways essentially. One is through the discounted factor, the other one is the average. For the average, if you take essentially the average rewards, then this Folk theorem is talking about some kind of possible equilibrium payoffs in this case. Again, it does not give all the things, but gives some reasonable concept of settlement. Let's do some definitions first. The first thing that I wanted to talk about is this feasible payoff profiles. So a payoff profile R is feasible if it is a convex rational combination of G's possible outcome. So this convex combination is, and again, we are talking about the rational, means the coefficient should be rational numbers. That's a very useful one. What's the definition? It says that for every action profile AJ, there is a rational non-negative number Cj, such that some of these Cj's are equal to 1, and then if you sum over all this, essentially take the weighted average, it becomes R. So this is generally the concept of convex combination. What's the meaning of convex combination? It means that you have some multiplicatives, some CIs, that their sum would be equal to 1. And then you will take the weighted average based on this. So two things, weighted average according to some coefficients, but the important thing is that the sum of these coefficients should be equal to 1. Good. Let's see some examples. Of course, what is the intuitive case here? It means that there is a finite sequence of action profiles for which the average reward profile is R. So what's the meaning of that? So if we have this kind of things that, like, again, some of the CIs should be equal to 1, and then if you sum it up, if you take the weighted average over, this would be R. What is the intuition is that if you are doing a finite sequence of action profiles, and this CI is the percentage of the time that you are doing each of these actions, then your payoff in that case would be R. And again, here note that we are talking about action profiles. Action profiles means that it's a vector of essentially all these actions. So what's the meaning of that? So it means that, so you are taking some actions, maybe this action profile. So this has two things. This action profile, maybe it is a different action profile that you are taking it, but again, maybe this one you are taking it more. So these CIs essentially are the percentage of the time that you will take these action profiles. If you take this percentage of the action profile, then the average would be the one that essentially you are looking for. So again, this essentially means that in a finite sequence of action profiles, the average reward would be this R, because this CJs essentially say what is the percentage of the time that these actions you have, this action profile, not just action, your action, the whole action profile has been essentially chosen. So, for example, in the let's see the definition for now feasibility, and then we will talk more. So, in the prisoner's dilemma, for example, you have this one that, I mean, the U of CC, the payoff of CC would be 3 and 3. And again, this is action profile. So you don't consider just your action, but the actions of others. So U of CD would be 0, 5, U of DC would be 5, 0, and then U of DD would be 1, 1. Good? So in that case, then if you can say 1/4 UCC, 1/2 CD, and 1/4 DC and 0 DD, then it would be 8, 4, and 3. So this one, so 8, 4 would be 2. So this is a feasible thing. Why is it feasible? Just look at this one. Here, this is the percentage that I mentioned. So here it says that 1/4 of the time you will do CC. So this is 1/4. 1/4 of 4 would be 1. Then we said that 1/2 to CD. 1/2 means that you are doing 2 by this one, correct? 1 and 2. So that's essentially corresponding. So this is corresponding to this. This is corresponding to this. And this DC is corresponding to this. So if you take all of this one, then the average payoff, if you compute it essentially, and especially if you just keep this sequence forever, then the average payoff would be exactly this one that we talk about, 213. That's the reason that we are talking about the feasibility. Here you can, I mean, check that 5, 5 isn't feasible. So because there is no convex combination that you can produce, you can write some equations, because these are some of the equations. You can give it, for example, to Polyp or others and say that there is no solution. Because you can do some system of equations. So this always, we will come to this system of equation that a linear programming, or generally a system of equations, is a special case of linear programming that Polyp, for example, can solve it, can just solve it and say, oh, there is no way. And of course, pi over 2 and pi over 2 isn't feasible because there is no rational convex combination. We talk about rational because why we talk about rational? Because we want to say what are the percentage of the time that you are taking it. If it is essentially irrational, then I don't know how many times you can do it such that in a sequence. This is impossible. That's the definition of rational versus irrational. So that's the definition of feasibility. Good. There is another concept, enforceability. So what is an enforceable payoff profiles? So a payoff profile R equal to essentially R1, R2, R1. Again, when we talk about the profile, means an essentially vector of all profiles. Is enforceable if for each I, Ri is greater than player I's minimax value in G. So Ri, the payoff that this person gets in average, is, and again, we're talking the average regime, not the discounted thing, in the average. So Ri is the player i's min-max value in G. Good. What was the min-max? It means that if everyone else, or like if there's two only other person, but if there are more than that, it means that there are several other players. If they gang up against this guy, they can make sure that this person suffers. That's the meaning of min-max. You try to minimize the maximum that this person can do. So what is the intuitive meaning? So this one is enforceable. That is the definition. So that's a simple definition. Why do we have this one? This is the idea that if there are, two or more than two players, if agent I deviates from a sequence of action profiles that produces R, so this is essentially R is agreement or settlement thing. So if you, and that was the whole idea, that if you repeat this one, because it is a feasible, you can produce it. No, I want to make sure that no one deviates from that, because this is some kind of equilibrium. So, okay, this is the feasible thing, so I can produce this sequence, and this gives you this average. But I want to make sure that no one essentially deviates from that. So if I deviates from the sequence of action profiles that produces R, then the other agents can essentially gang up to punish I by reducing I's average to some number, essentially, which is the average reward can be at most the I's min-max value, because they can all gang up and make sure that this person gets the min-max value instead of some other value Ri, which is higher. So we knew that because these Ri's are greater than this one, if this person cooperates, it gets something better than min-max. That's by definition. Better or equal. However, if that person deviates, then other people can gang up and make sure that that person gets min-max. So essentially would be that would be a loss for that person. So that's essentially, as I mentioned, so these other agents always, they can force it, essentially enforce it by doing that. So this is the generalization of the Grimm strategy. If any agent I deviates from the sequence of actions it is supposed to perform, because as I mentioned, there was some feasible things that you could do it, then all other agents gang up to punish I forever by playing their min-max strategy against them. So that's essentially the repeated game. So we have the feasibility that there is a sequence that can produce this average, and then we have enforceability that if somebody wants to go away, then everyone essentially makes sure that they can punish that person. So this is essentially the main intuition. You can make it more formal, but this is the Falk theorem essentially that say the Falk theorem that says that if G is finitely repeated game with average rewards, if there is a Nash equilibrium with if there is a Nash equilibrium with payoff profile R, then R is enforceable. So we say that for any Nash equilibrium, if there is some kind of Nash equilibrium with the payoff, hereby a payoff profile means average payoff. So this is average. So this is the. So if this is with average payoff profile R is almost enforceable.
You said almost.
No, R is enforceable.
Oh.
Yeah, and that essentially comes from this one. You can just use the definition of min-max and the best response to show that in every equilibrium, each agent's I's average payoff is greater than I's min-max value. So there is if you put the definitions, I think you can. If you put the definition, then you can prove that. This is like a good exercise to work on it. But this comes essentially from the definition. So if it is a Nash equilibrium, then R is enforceable, and this is vice versa. If R is both feasible and enforceable, then there is a Nash equilibrium with payoff profile R. That's essentially the things that I have mentioned. So we can construct a Nash equilibrium that gives agent I an average Ri. How can we do that? As I mentioned, because this is enforceable things, because it is feasible, there is a sequence of moves that the average would be this. So you will take that one. This is a sequence of move, and that's things. And then you can make sure that no agent can do better by deviating because the other agent always gang up and punish that person. So that essentially comes from this definition, the way that I have mentioned. So this is called a Fogg theorem. And this is the one that essentially said that in this kind of repeated game, you see, the people considered more general setting and said that, can we prove some theorems there? The theorems become more non-trivial because in one game, one shot is much easier to consider repeated game, and not even with a finite number of stages, with the infinite number of rounds or stages. But this is some kinds of concept that you can use it essentially and define a concept of touch equivalent if you want to construct it. As I mentioned, that is just one. There might be lots of others, but we say that here, okay, we cannot find everything, so that is one reasonable thing to take. Good. You can always think about it. This kind of, when we talk about infinite things, you can think about, consider a finite game, but this number of iterations can be very large. That at least, I mean, probably they can be different, so in theory, they can be different, essentially. But lots of the time, practically, these are the same. For, like, as I mentioned, for iterated prisoner dilemma, these are the same thing, essentially. And this has been used essentially widely to study the emergence of cooperative behavior among agents. In particular, this is I believe this is a book actually, or article, but it should be a book. The Evolution of Cooperations by Axelrod. That he ran a famous set of tournaments. So people contributed strategies encoded as computer programs, and Axelrod played them against each other. So like you may have a complicated things, I mean, anything. Some of them we discussed, but these are not all of it. And of course, I mean, this is always this concept is in the mind of the people because of this iterated things, that if I defect now, he might punish me by defecting next time. That's essentially the whole concept of this iterated prisoner's dilemma is based on this concept, that if this is the main essentially challenge that the people need to answer it essentially in any things that you are doing. So as I mentioned before, in this study, in Axelrod's tournament, tit for tat usually did the best. And it is, again, this is something that works quite well. It could establish and maintain cooperation with many other agents, and it could prevent malicious agents from taking advantage of it. As I mentioned, this is very important, these both things, because I don't want to be essentially a dumb person and just everyone is doing that. Forgiveness, I mean, has some limits. And if you, sometimes actually it's better to don't forgive because it's better for that person, because that person may go with some other people. And it might be the other people who are not so much forgiving, and that might be much worse effect. So there's a limitation for forgiveness. As I mentioned, this tit for two tats things that we talk about it. That's the one that has a little bit more forgiveness. But generally, this tit for tat actually works very good, that if you cooperate, I cooperate. But if there are some malicious players that they want to take advantage of me, then no, I will essentially react. And you can see essentially what will happen. For example, this is actually a good thing. So if you do it with all the tit for tat, then also you are doing the. If you are doing this cooperate, then you will cooperate all the time. And if you do it with the tester, just mention to the tester, oh, don't test me, essentially. Don't try me. If you try me with some defect, then I will react, and then you will suffer. So that means that, okay, we are both going C, essentially. And even there are... this is a real-world example of iterative prisoner dilemma described in the Axelrod book. Actually, as I mentioned, that was the book. So it was in the World War I trench warfare. I don't remember the exact countries that they had it or the different parties here. But this is the thing that happened essentially. This kind of repeated game, actually, you could interpret there. So this was essentially two infantry that they try to essentially fight with each other, and then this was the idea. So they had this prisoner dilemma in general. It is very important because it talks the concept of defect versus cooperations. There, in this one, it was not prisoner dilemma per se, but it has a lots of similarities. So here, there are incentives to cooperate, essentially. What's the meaning of that? So he said that if I attack the other side, then they'll retaliate and I'll get hurt. If I don't attack, maybe they won't either as well. So in some sense, this is very important. Prisoner dilemma is just maybe some game with some normal form matrix. That is not the main point. This is the thing, some real world things that talks about that if you both cooperate, then we can get something. But if you defect, I mean, then essentially you can consider, as I mentioned, two neighbors or husband and wife, essentially, two spouses in general. That, I mean, if you try to, I mean, forgive and be good to the other person, that would be good. But if you don't do that, then both of you suffer, essentially. So it is a real world situation. And this was the result of the evolution of the cooperation. So this was the case, essentially, that the historical things that also two infantries were supposed to be enemies. They avoided attacking each other because of these things. So they could actually do that, but each one said that, why should I go there and get hurt? And nothing happens. Good. So I think that's the things that we wanted to cover here. So we talk about, I mean, finitely repeated games. Then we talk about the infinitely repeated game. As I mentioned, this also happens in practice, and these kinds of cooperations, and this one is like an extended general, like this is a generalizations of the concept of prisoner dilemma into some war situations. So there are some, these are real world situations, and you can use it. These strategies that I mentioned, you can actually consider them when you play game. Again, this is not a game that you are doing chess, but this is the way that you are talking with your neighbor, you are talking with your spouse, you are talking, I don't know, with your professor, with anyone. You can take all of this. Good. So I stop here.